Hello, community. So great that you are back. Yeah, artificial intelligence is becoming a little bit confusing, don't you think so? Just look at this for context engineering in multi-agent system configuration. Now, Google decided, you know what? We need a complete new mathematical theory for this. And here we have it. This is all that you need to know about artificial intelligence. This is here the definition of an agent in a new probability space. And we will have a detailed look in this video today. Now, if you're interested how this is now a representation or an optimization problem in a mathematical space, if we have two interactive agents, we just have to solve this simple optimization problem. And yeah, this includes almost everything that you know. And we can really call this a grand unified theory for multi-agent optimization. And you know what? This includes a standard agent, which uses your typical large language model here, a functional LLM, to decide here on the output. And of course, this is a probabilistic engine. But it also includes here complete tool use cases. No? And a tool is simply a special type of an agent in this integral, where the functional F code is a Python script or a C++ or a supercomputer simulation in the background. This, of course, is a deterministic agent. Welcome to my channel, Discover AI. We have a look at the latest research paper, and yeah, I already prepared you for this because I built here on this in my last 5 videos, and you will see it is real simple to understand the new theory. Now, you know, in my last video, we talked about LIGO gravitational wave tokenization here with a large language model. I have multiple videos here on DSPy here for if you want prompt engineering and optimization. We talked about a probability functional already. Context engineering, we go to the next step, to the next abstraction level, and we will finally explain here all the technical terms and the complete flow diagram of the latest ADK processes here by Google, because Google here on December 4th, 2025, architecting efficient context-aware multi-agent framework for production. So, a new multi-agent framework by Google with the complete code. But we need something that we can understand it, because it is not as easy as you might think in the first place. So, you know, if you want to build today an AI agent or multi-agent, you have thousands and thousands of variations. So, you have everything from a control flow mechanism, which more or less partitions here the action space and guides here the agent through a predefined graph or a state machine, thereby constraining its behavior to improve the reliability of the system. And on the other end of the spectrum, you have a random walk nature. This is a basic React loop, which, while it is flexible, it can suffer from a lack of convergence, and even more important, it regularly falls into hallucinatory loops. So, therefore, you know, prompt engineering was a year ago. This year was about agent context engineering. And now Google unified everything and built a complete new mathematical optimization theorem and the complete code implementation already for you. So the very context provided to the agent is what? It is the initial prompt, it is all the available tools, and the method of updating its particular state with any new observation, with any new data. Therefore, the context for an agent is a critical design element. Now, if you've heard this year, all this context engineering, it can be divided into a static and a dynamic approach. Static, you're familiar. This is the very old prompt engineering approach. Or if you go dynamic, where the state is strategically manipulated, summarized, or selectively updated at each step. Now, the second is, of course, much more interesting, so let's have a look. In my last video where we talked about, hey, in astrophysics, if we have two black holes spiraling here closer and closer together, we have a beautiful gravitational wave signal that is really here, going here for millions of light years. And we on Earth, we can detect it. We have a real complex signal. And in my last video, I showed you we can tokenize those gravitational interferometric patterns with a simple tokenization engine. And then the LLM is doing all the work for the detection of this gravitational signal for us. And I told you we were swapped out here the functional form of a convolutional neural network to a transformer network, because this transformer aligned here the mathematical topology of the model with the real-world physical topology of the features of the gravitational wave. And this was exactly what we needed. So you see, you already know half of the solution. I already showed you this in my last video. Okay, so the Google Agent Development Kit, ADK, is an open source multi-agent native framework built to make active context engineering available in real production system. So Google is not just producing here Gemini 3 Pro, but also a complete new way how to build the perfect multi-agent system. And Google tells us, hey, we cannot optimize what we cannot mathematically define. Absolutely correct. So Google therefore provides a grand unified theory of AI agents. This is the paper that you need to understand the ADK. Here we have it, here December 5th, 2025, Google Cloud AI, a beautiful introduction into the mathematical framing for different agent strategies. This is the future of AI. Of course, it also contains a mathematical proof why DSPy works, but I think you are not really interested in this, because if you want, we have now a DSPy system for multi-agent configurations and beyond this. So let's have a look. Imagine now in your old classical case, you're trying to build a robot that has a function of a butler. No? So currently most AI engineers build this robot by prompt engineering. No? They write here a note that says, hey, little AI, you are a butler, please fetch my coffee, then clean the table, and then do this and that. And if the robot fails, then they just edit here, no, the input. No? They say, hey, you are a helpful butler, so, and whatever went wrong. Now, Google is telling us, stop treating the robot like a magic black box. This is nonsense. This is science. Treat it like a probability machine. We have the mathematical formulas for the probability machine, so therefore treat it like one, and therefore you can optimize it much better, much faster, much cheaper. Okay, so this paper is telling us here, or providing us with the equation to calculate here the complete new probability theorem in the complete new probability space, and it identifies exactly which levers, which parameter you can turn to improve your probability densities and your success. Google identified 5 distinct components to any agent in this new framework. You know all of them. C stands for context, no? This is the input reality. In my last video, it was the gravitational wave spectrum here of a collision or spiraling in of 2 black holes. F stands for the inference functional. This is, if you want, the brain, or a specific LLM, a Llama 3, a Gemini, whatever you have. And this is here an engine that processes information. And it can be a vision language model, a vision language action. It can be a diffusion model, a number 2. It doesn't matter. Then we have the state, S. This is more or less the memory. What does the agent know right now? And this will hopefully evolve over time and develop. A is for the interaction and for the action with the environment. This is simply the output of our agents. It can be a tool call, a final answer given, or an internal sort process. Finally, we have the update function, U. This is the scribe. This is the logic that decides how to write new action into the memory. Does it append everything? Does it summarize us here? And we will have a close look at the update function and how we can optimize it. So this is the definition. Those are the components of an agent we're going to optimize and integrate if we want to optimize the configuration. Now, Google tells us that the core insight of this paper, of this mathematical paper, is that any AI agent is, in principle, a Markov chain of probabilities. A chain of probabilities. So if an agent needs 3 steps to solve a problem, like thinking, use a tool, and then answer, the total probability of success is, of course, as we know, the product of the probabilities of each single step. So here you have it. This is the complete probability, given we have a context C, and we derive at a particular answer A. And you see, this is, if we have this 3-step problem, this is here the formula. S0, S sub 0, is our initial state. This is our prompt engineering, if you want. This is the very beginning. What has the memory? At the very beginning, you only have a system prompt or maybe a user prompt. And the probabilities that are shown here, that the model f, our functional, picks here the right action, A, particular I, given what happened just before here with the state at I minus 1. So this is our typical definition. Now, this mathematic explains why the long horizon agents typically fail. If you have really a deep research agent with multiple steps, they fail. Why? As the chain grows, the probability decays towards 0 unless each step is near perfect. And if you have something that collapses to 0, you know in a multiplication, you know exactly what happens to your overall probability. So Google looked at this and said, okay, so what can we do? They invented a new concept of degree of freedom. Now, those are all the variables you are allowed to change to fix here the probability chain in a higher dimensional complexity. Let's have a look at the simplest one. The basic agent is your React loop. So in the standard React agent, the loop is fixed, and what you can control is only here, more or less here, the state at state 0, the system prompt given at the very beginning before the system starts. The trap is, of course, you are trying to solve a complex dynamic problem with an initial static instruction set. So if the probability dips in step number 10, you can't intervene because here the ground truth, here the state as 0, is too far away for you. So therefore, multi-agent system, no? The advanced agent configuration. This is now where the mathematical paper of today connects to the gravitational wave insights of my last video. Because this multi-agent system now introduces here an action partitioning in the action space itself. So you break here the big chain into smaller, separate chain if you want to see this in a very simplified pictures. And here we have it. So you see now our, if you want, probability of success is now an integral over 3 main terms. If we look at it a 2-agent interactive system, so let's say agent 1 delegating to agent 2, or some say agent 1 is here a supervisor and agent 2 is the worker, whatever you like to see it. Now you see now, again, we integrate over context, which is now absolutely fascinating. So let's see, agent 1, then we have a handoff and agent 2 is working. So let's have a closer look. What does this formula mean? Now, in the background, you know exactly what process we want to map this to, no? The last video showed you we have here the gravitational interferometric data coming in from the gravitational black hole spiraling process. Then I told you we simply have a constant quality transformation as CQT. Then we have a time frequency spectrogram. We do here a k-mean optimization to, if you want, develop or assign here specific integer values to our shapes. And then we just have here a normal tokenization process of our 3-dimensional gravity wave that is entering now here our LLM. So what you see here, the magic variable here is, of course, here our context here, CL. This is here the context for the sub-agent. If you want, this is the new degree of freedom we can now integrate over and therefore have a mathematical optimization problem where we find new mathematical solution to this. Agent 1 doesn't just call agent 2. Agent 1 generates here a very specific context and instruction set to maximize agent 2 success. And this is now not done by you, a human being, but this is itself a part of a mechanical optimization process if we do the mathematical optimization given Google's new agent framework. So if you want to see this, you see here our CL and our CK. Just to make it clear, CL is here the link context. So this is the input passed down from the supervisor or the agent 1 to the sub-agent or the worker agent. Those are just the instruction telling here this agent 2 what exactly you have to do. And of course, we have then a result reported back to the supervisor, or you can call it here context kernel or knowledge context. And this is the output passed back up from the sub-agent to the supervisor agent, or the report or the return value, however you want to call this. So clear, we have up and down communication pipelines. Great. Now, interestingly, if you look closer at this formula, you see that we have included here also a CK here in the sub-agent reports. And you see, why is this suddenly in our integral for the integration here as a probability term? Now, the answer is simple. The authors included here CK as a probability term because communication is lossy. And just because the sub-agent found an answer, or an action here, K, that it reports back up, it doesn't mean it successfully communicated it already to the supervisor. Because sometimes the AI decides, hey, I found a result, but I'm not communicating to this particular agent, but maybe to the memory or do something else with the result. So you just have to be always aware this is a statistical system. This is not a deterministic system. So yes, you have also take care about the probability that the communication is not reported here from the worker agent up to the supervisor agent, which is just amazing. Google thought about this and integrated this into the optimization process. Now, the particular term here, the probability term here, forces the methodology to optimize the return protocol. So we want here the sub-agent to generate here a context here that creates here the best state for the supervisor to finish the job. So you see, this is now an optimization methodology and algorithm that not only the supervisor has to find the perfect prompt engineering with a context engineering to define the new job for the worker agent, but also the result that the worker agent finds with its particular domain knowledge. Let's say this is a worker agent in theoretical physics, but a supervisor is not a theoretical physicist agent, but just a general science agent. Then the agent 2 has to provide here the best state for the supervisor to finish the job. This means the communication form, the shape, the context that is now selected as a result that is reported to the supervisor has to be optimized in a text. And if you think, hey, how do you optimize a text? Well, I'm gonna tell you in a minute. Okay. Yeah, of course. As I told you, this is a complete mathematical new framework, a grand unified theory. So, of course, it integrates all the function calls that we know, and we have to do maybe manually, or we have whatever, MCP protocols, whatever. So, this is not in the paper. This is just that I want to demo you my understanding what is happening. So let's really do a simulation of the function call structure. Now here's the sequence that I imagine. Agent 1, our supervisor, analyzes here the situation, my prompt, and decides to delegate here the execution of the job to an agent 2. So it produces now a very specific context here to be handed down to the agent, the worker. For example, it says, hey, go analyze here from my last video the gravitational wave data for a particular timestamp t. Now the sub-agent or agent 2 receives this context here. It performs now, given this particular context and its inherent understanding of the context, and it performs now a particular action A. And now there's also a probability density distribution. Action A1 or action A2. Now it decides now to perform a particular action A, and this is doing the heavy lifting. For example, like in my last video, it runs now the Llama 3 gravitational wave model I just showed you in my last video. Okay, agent 2 finishes, done, gets a result. A highly complex result in its particular domain. So it must now communicate this result back. So it generates now a context K based on its action, based on its understanding, and based on its result. And let's say the result is I found a signal with 98% confidence that this is a gravitational wave event. Agent 1, the supervisor, receives now the generated CK here, and given the understanding what is this context, what is the data, what is the information, it updates now its own state as given the new CK, and it continues now with its own work, with its own action here as a supervisor. And what is the job of a supervisor? Now, Juba says, okay, since the signal was found, I have the context CK. I will now email this observatory to the human beings that are waiting for the results. Okay, just that you have an example that you can work with, this is how I imagine this. Now, in Google's ADK, of course, just to give you here a hint, CK corresponds here to the tool output. I told you we will have standard agents and tool, which are also special agent. Now, in the ADK, and this is important because it has a very specific technical terms directory, what CK is an artifact returned by a subflow. So careful with the new notation, but I will explain this at the later half of this video. Now you might say, hey, where does the model context protocol MCP fit in? MCP, think about it, provides a set of tools, a standard syntax to shape how the arguments are produced by a model, as well as support for a kind of a prompt template to use in the shaping of the state that is consumed by the model. So in a kind of way, it allows the models to be trained to improve the probability by improving the order with changes here for the update function here and the new state configuration. But yeah, now this changes immediately if we look here to Google's agent-to-agent protocol. Because look at this. On the other hand, it provides a pathway, what a coincidence, to building here an algorithm to optimize specifically for CL as well as a medium for CL to be passed on, action K to be executed, and CK to be returned to the supervisor. And this is so coherent in the algorithm, what a coincidence. Therefore, by allowing the agent to be developed within improved odds, by changing here our functional, our update, and our state, agent-to-agent allows for an easier partitioning of the action space in a way that will likely lead to a higher probability of outcome. This means to better results of your AI system. Do you get the wink? Okay, so Google, absolutely amazing at the current point. Just want to tell you, in this new framework by Google, there's no mathematical difference in this new mathematical framework between calling a tool, like a calculator or whatever, and calling a sub-agent, like a researcher. It is absolutely no distinction anymore between tool and sub-agent. Everything is integrated into a new grand unified theory of multi-AI agents. Okay, I think this can close now the chapter here, function call structure. Great. So, coming back here to our main formula where we integrate here over all the different form of context and all the different variation and all the different communication patterns and communication channels. And with this new degree of freedom, just a word, you can also make it simple. If the collaboration pattern between the two agents is just two agents chatting about the latest, hey, how is going to be the weather? Or I don't know, my user asked me what is news or whatever, then you can manually write the system prompt for agent A that is simply, hey, please explain this to agent B. So then you do not have to find a highly complex mathematical optimization procedure for some simple gossip. But if you work in science, and if you are real, if you work in finance, in medicine, wherever it is really important, it is not social media AI, the situation changes now significantly. Because if the collaboration is now mathematically defined and has a clear target, you can see this as a probability term. Then our context, the context being passed down, is now a variable we can integrate and optimize for. So this optimization integral becomes now real powerful, but also real huge. But if the moment the CL becomes now a variable in our mathematical framework, this means we can use now all the mathematical algorithms for the optimization that we use and that we know to search for the optimal CL. So we have an optimization process within an optimization process mathematically. Now we come to DSPy. Because, you guessed it, yes, this is of course here Lean 4 DSPy. Yes, you see I have some videos here 4 months ago and a playlist with 10 videos on RAG and DSPy and graph and multi-agent topology DSPy just 9 months ago. You got it. So with DSPy, I told you almost 9 months ago, we stop writing prompts as human. No? We just define the metric, we define what we want to achieve, and the system compiles here the perfect agent interaction here on, if you want, a prompt engineering level. Now, I ask you here today, December 7th, recording this video, how do you use DSPy? Yeah? And after 100 votes here, this is the result. So, 1/3 of my audience tells me, I ignore DSPy. And I understand why you ignore DSPy, honestly. 42% tell me I like it, okay, and only 25% tell me I love it, and therefore I guess that I use it regularly. So, DSPy is essential to understand because we will build on DSPy ideas to further, standing on the shoulders of giants, to make the jump to the next level of complexity. So let's talk about a little bit about DSPy. Before this mathematical paper here, by December 4th, 2025, multi-agent systems were often just, hey, I take 5 copies of GPT-5 talking to each other, and this is my multi-agent configuration. Eh? This new mathematical preprint now exposes here the term the functional f. This means the invariant functional as a variable. What is it? It is just the model. Do you go with a Claude? Do you go with a ChatGPT? Do you go with a Gemini? Do you go with whatever? The inference functional is now a variable you can integrate and optimize for. And this proves mathematically in the paper that for a certain step here, the probability is maximized only if you swap the model. So, we have now a mathematical optimization procedure that you do not have to work with 5 copies of GPT 5.1, but with models that are optimized for the size, for the cost, for the performance, for the tools they will use, and for the interaction patterns with other agents, and overall for the complexity of the human task, the human job that was given to the AI. So this turns out that the model selection turns now into a real mathematical optimization problem that we can solve in this new mathematical framework, and it is not anymore a vibe check. Hey, today I take Claude Sonnet. No, not anymore. Or you think, I think having a critique agent, no? The topology of your multi-agent configuration. Let's insert another agent, yeah? Maybe it helps here, no? This is gone. Vibe topology is not a thing anymore. The new way, the mathematical correct way is now, we treated here the interaction content as a hidden variable and optimized it via a stochastic search, finding that a 50-token summary yields higher probability than the full log of the communication. And these are simple goals that an AI can find out themselves in the optimization run, where we do not need to interfere as humans anymore. Now, of course, you understand we have to go beyond current DSPys. Ne? While DSPy focuses heavily on optimizing here the text here, if you want the prompt here, which is our S0, and the examples, the few short examples that we provide, DSPy was beautiful. But now Google decided to go the next step. So this mathematical paper argues that in DSPy, we were just ignoring the other variables that were already there. Why haven't we taken care of the other variables? And Google now tells us, okay, let's do this. So the current DSPy lets you optimize more or less just here the prompt complexity. No? But this new mathematical framework also tells you should mathematically now optimize the functional. This means the framework implies the optimizer should be able to say, for this specific step, Llama 3 is yielding a low probability. I'm mathematically swapping this model to a Claude 3 Opus or any other fine-tuned model in my own library that I have, where I have here the performance features and here the performance indicators that are essential here for my domain, like theoretical physics or mathematics or chemistry or biopharma or whatever you have. Then you should optimize here the update function. This is, you remember, the memory. You should optimize also the structure of your memory, the content of your memory, and the representation of your memory. The simplest question, of course, should be, should we append here the full history, summarize it? We choose this currently manual. And the mathematical framework tells us, hey, this is just another variable theta that can be learned by the system. So we as humans in the future, we don't have to take care about memory optimization anymore if we solved it here in a beautiful, clear, generic memory update functionality that takes care about everything I told you. And of course, the complete topology of our system, the graph. Is it a chain of agents? Is it a parallel? Is it a swarm configuration of our agent? Do we have a supervisor? What are the functions of the supervisor? What are the communication channels between the agents? Is it also a vertical communication line established? What are the limitations on a communication channel? And. This preprint by Google really frames here the shape of the graph, the interaction pattern here as part of the probability integral, and therefore we can optimize for this particular topology. Now, DSPy gave us just the very first tool to do this. DSPy was just the beginning. Now, in this preprint, I think we have a grand unified theory. It suggests that in the future, we don't just compile the prompts, like DSPy does now, but we will compile the entire agent architecture for our system. Not we, the system will compile it. An agent will find for my particular job in theoretical physics, where I say, hey, I would like that it costs less than $10 here, my job to run. It will tell me which agent, in which configuration, how many agents, what are the complexity, how we subdivide here the probability space into subspaces, what models are best here suited here to come to a fast and an accuracy that I defined with 98% solution. So you see, this is a mathematical optimization. Why should a human do this? So, main new idea, what I really loved about this paper, this is it. This is the definition of an agent that includes all the tool use, everything. And it is defined in a new probability space, P. So what we have, A, our actions, no? The sequence of actions, the output we want to generate. C, as I told you, the context, the input data, the raw gravity wave data. No? U, the update function, how the memory is handled, memory size, memory complexity, memory representation, memory compression, everything. F, inference functional, the model architecture. Now, the cooperation is calculating the probability of the next action given the historic state of the system. No? The critical point, if you want, is that our functional dictates how the state influences here the action. Of course. We did this already, that without me telling you this in a mathematical framework. I explained this in my last video. You remember? We had the gravitational wave data. We had the tokenization process. I told you I swap out a functional A. This was our convolutional neural network. I substituted it with a large language model that was based on a transformer architecture. And given this swap, swapping the probability functional, now you know what I mean, and we could reconstruct the pure waveform without any noise. We could see here really the gravitational event that we were looking for. So this means our probability functional convolutional neural network is simply calculated here, based here on a narrow window, as I explained to you, given only that we have here a window sliding here over our complete spectrograph. And we choose here to move here from a CNN to a transformer architecture because the transformer calculates the probability based on a global semantic relevance, the self-attention, and this was the reason using this model that we had to use a tokenization process here. So you see, everything is connected with everything else in this chain of data pre-processing, data processing, analyzation, and which tools I need, what are the complexity of the tools, how can I combine the tools. Everything is just a mathematical optimization. And in machine learning, we often are obsessed over parameters, our weight optimization, over the dataset size that we need, or compute and flops, but we rarely think about the structure of the probability space itself. But now we do. Now Google put out a new framework and says, this is the way to do it. Now, I just remember I had problems in the very early days of DSPy because I could not, for example, understand in the explanation of DSPy in the first day, they talked about a teleprompter operability, and I could not understand what is a teleprompter doing in DSPy. And then some weeks later, they told us, hey, you don't write prompts anymore, no? You program prompts. And I said, what? I have to go now to C++ and program my prompts? So there was a big misunderstanding that originated here with DSPy in the very first day for me personally. And now I want to take care that this is not happening for you in this new mathematical framework by Google. Another idea that I had in the very first days, I said, wait a minute with DSPy. So we just have to go and trial and error to explore the entire solution space to find here the optimized prompt engineering. I mean, this will be expensive, no? This will run for days and weeks for the complexity of my jobs, no? What I completely misunderstood in the first days, that they built on a gradient-based optimization of the system itself. What was the core hidden concept of DSPy was exactly the gradient-based optimization, of course, backpropagation. So we did not just try different parameters and say, oops, this failed and this failed and this failed. We assumed that the parameter space is smooth and thereby differentiable. So therefore, we can provide your mathematical operators to work on this space. So the idea is so simple, but I couldn't get it at the very first days of DSPy, no? Because if we change here a prompt slightly in a direction A, and the results gets better, we don't need to check for any other direction B. We just run towards this direction A. Now this explains the problem I had thinking, hey, we have to explore the complete solution space. I mean, this is so expensive, no? No, we already had a restriction with this. And in the agent framework, it's not the same. Even though the agents are discrete, this means text-based, integer-based in their tokenization, we can treat the optimization of the context, our CL, as a gradient problem. And the same is true that happened to me in misunderstanding DSPy. And therefore, I want to make it crystal clear that we do have an internal optimization already in place before we even start. We don't have to do trial and error in this new mathematical framework by Google, because we're going to show you just a few step-by-step samples, which are the direction that leads to a better verifier score, and we push the system in that way. This means we already have an optimization procedure. Okay, this also means for the optimization here, we don't explore all parameter, but we Google, explore in a smart way. So, you know from theoretical physics, hey, if I have this integral and you integrate over all possibility here of the context that is reported back to you, I can't solve this integral. How should I be able to solve this integral? So what we do in theoretical physics, we have a simulation or a Monte Carlo shortcut. So the integral in the preprint looks a little bit scary to me, but I know in physics when we have this kind of integral that I can't solve, we use simply a Monte Carlo integration. No? So instead of checking every possible pixel in the gravitational wave image, or every possible sentence context CL, we just sample a few key paths and we learn from these few key paths, hey, what is working? Up, down, left, right, direction A or B, or where we will go. We just start simple, baby steps. We don't sample pure randomly. We use the LLM's own probability distribution from the pre-training to guide here the sampling process itself. So this means the model already knows that 99% of the parameter space is garbage. So it creates inherently a guided search that ignores the nonsense and focuses only on the plausible actions. And you know, those actions are not somewhere in a three-dimensional space, but they are all located here. You know this, I showed you this in my last videos, on a high probability manifold. The tiny slice of the universe that really makes sense, but not the whole parameter space. Because only this little golden band here, this only hyperplane structured manifold, contains all the solution and is therefore the high probability manifold that we are looking for. Ignore just the complete rest of the parameter space, of the solution space, of the probability space. Okay, if we understand this, if I understand this, okay, that we can now explore this smartly, we have now the gradient-based optimization that is also now taking place in this new mathematical framework. So even though the agents are discrete, producing text pieces, no sentences, human sentences, we can treat here the optimization of the context, our CL, as a pure gradient optimization problem that we have the mathematical solutions for it. We have the formula for this. And we take a few step-by-step samples, we see in which direction we have here the best verifier score, and then we push the system in that way. And I do not have to explore the other 359 degrees. This is not necessary. We just believe we just have to find here the high probability submanifold in our complex space. Also for the generalization from few to all. Remember, in my last video I showed you switching here the probability functional from a convolutional neural network to a transformer network already reduced the whole search space. And I showed you that they just trained here LIGO on 90 real gravitational signal samples. So the space of possible black hole mergers is, I guess, infinite. No? But for training our little llama model, it was enough. 90 real-world physics samples were enough that the system learned how to detect gravity waves. Why? Because the functional generalized the structure. We have chosen a particular probability functional where the topology of the functional, the operation of the functional, was coherent with the data topology. And the data topology of a convolutional neural network with its little sliding windows was not enough to have an analysis of the spectrograph of the wave pattern from the beginning to the end. So you see, this is the explanation why it works. So we do have to search. No, don't misunderstand. We do have to do some search, but we are not searching for the answer to every specific question. We are just searching for the optimal policy. And policy here in learning means the strategy, how we find the right path forward. Now, a bad search would be trying to find the answer to every mathematical problem one by one, infinite space, infinite costs. But a good search would be exploring the parameter space until we discover the abstract rule, hey, whenever you are stuck to calculate something, just call the calculator tool, because this is a deterministic engine and not a probabilistic engine, and this will do the job for you. So you see, my mistake with DSPy was, I was a little bit afraid that it would get too expensive too soon, because I was thinking we need to explore the complete space. No, we just have to find here this high optimization manifold, have a direction, and then go in this direction, we will find a better solution. So don't make my mistakes. Yeah, last video. Data pre-processing and gravity wave tokenization. Here as a multi-agent system, you can imagine this immediately. This is an agent with these tools, the QCT tools, or an agent here with these tools, here the k-means optimization. So you see immediately my last video, I showed you here multiple agents. But of course, I told you in this new mathematical framework, a tool is also here a special agent. So you can play this in any combinatorial density that you want. Great. Now, again, the functional, the model as an optimizational variable is something brand new, because in the current DSPy, we assume that the model here is fixed, that this is an engine, we cannot do this. So you optimize the instruction and the examples to fed into the LLM, into the machine, but you cannot exchange the LLM itself. Now, in this new framework, you treat here the functional itself as a variable to be optimized. So the system could now decide autonomous, hey, for step 3, pattern recognition, the probability P overall is maximized if I swap the generic GPT-4 functional for a Llama 3 gravitational wave functional for a particular fine-tuned Llama model, as I've shown you here in the second paper in my last video. So we are not just reduced to compiling prompts, but we are now compiling here the complete neural architecture at runtime for an optimization. Also, We have the update function as an optimization, as an optimizable variable. In the current DSPy, you define how the history is handled, no? Pass the last 5 question and answer pairs. Now in this new framework, the definition what is in memory and how it is optimized and how it is structured and how it is constructed and how it is compressed is fluid. The optimization, therefore, is this optimizer creates a gradient on how to remember. It might learn, let's say an example, for a legal task, I have to keep a lossless log because it is extremely important here for legal task here that I have here the perfect definitions. For a physics task, I can use here k-means quantization summary, like I've shown you in my last video when we were talking here about gravitational wave interferometric patterns. So, the memory mechanism in this multi-agent system becomes just another weight that we can tune and therefore optimize. And the system can learn. But of course, the collaboration topology is also an optimizable variable. In the current DSPy, you define a pipeline. No? You have model A and then you have model B. Done. In this new framework, the graph structure of the agent itself is part of the probability integral. This means the system can search the space of topologies itself. But the system can say or ask, hey, should I run as an AI 3 agents in parallel as an ensemble? Or should I define multiple series, multiple chains? Or maybe I go with a swarm configuration. What are my values that I learned here in the pre-training? What was my training telling me? What is the best optimal configuration? And if I have defined here on a minimum set, how can I optimize it further? You can find the optimal handoff structure automatically. You don't have to program how many agents you want, what is the interaction pattern, and so on. So, take a step back. We have a beautiful evolution of AI engineering taking place. In the past, we were manually prompting an LLM. We just guessed what words would be great for the particular job and our individual complexity for our domain complexity. The present, we have DSPy. It is more or less software engineering. No? We define a pipeline and compile here the prompts more or less. And now the future is we have a complete AI architectural compilation. So we define a goal, and this is it. And now we let the system optimize its pattern. And an architectural configuration is also a pattern. A simple prompt is also a pattern. The memory logic is a pattern. The memory structure is a pattern. The team structure itself, the topology of the agent, is a pattern. So I let the AI system optimize a pattern system and therefore maximize the probability of success. And Google provides here the mathematical formula to calculate here the maximum probability of success, given that all of those elements are now variables. And you might think, hey, this is just academic nonsense. This is just theoretical knowledge. And therefore, I was so glad that I found just yesterday here, Google for Developers, Google published this now as an implementation as code. Google released the code for this, what we just discussed theoretically, and they call it now, guess what, context engineering, but it is exactly what the mathematical paper predicted. We are now optimizing the state update U to optimize, save the probability chain, and further have a complete optimization of the multi-agent configuration. So Google is not giving us here the pure mathematical understanding, but already the real-world application, the real-world code. I love it. So Google ADK already compiles context. Isn't this absolutely amazing? Now, if you have a deep dive in this paper, and I highly recommend this, here you have the link for ADK, you see suddenly you have new terms. And I love if you have a new terminology, flows and processes and context processing as a pipeline. And every agent is backed by a flow, which maintains here, beautiful. And if I look now here and I say, oh, great. So what is this? Good. Let's start here. And because I think this is so important, because I noticed with DSPy, if I could not understand the technical terms in the first run, I developed here an emotional distance here to this DSPy module. So therefore, we have to get it right the very first time. So let's start. This is what Google tells us. Sessions, memory, and artifacts are the sources. Flows and processes are the compiler pipeline, and the working context is the compiled view you ship to the LLM for this invocation. Great. Now this doesn't tell me anything, so let's have it my way. So the gravitational wave preprint LIGO in my last video showed us why we need to do this. To beat the noise, we have to get rid of the noise. This mathematical preprint Google showed us that we developed a grand unified theory and all the mathematical formula for it. And now Google ADK gives us here the code to build it. So let's do this. All the ADK terms explained in the framing of the mathematical paper by Google. Otherwise, I could not understand it without the mathematical framework. What is an ADK processor? In the Google definition, it's a modular component that filters, transform, and inject the data. They run in a pipeline before the LLM sees anything. Okay? And what if we transfer this to our agent mathematical definition? Guess what? Processors are the state update functions. My goodness, it can be so simple. So therefore, just give you here a visual. No? In my last video here where we talked about this, in the gravitational wave paper, the K means quantizer here, this one here, took a noisy wave and turned it into clean tokens. So this was an ADK processor. Beautiful. In ADK, a compactification processor takes a noisy chat history and turns it into a clean summary. So you immediately understand what is happening. Those are noise filters. They exist to ensure the agent is operating on a high probability manifold. We cut here to the complexity of the solution space and we look at ourselves in a high probability manifold that is a much reduced subspace. And if you feed raw data, noise to the agent, it falls into this dark black something. So a processor strips the noise so the agent only sees here this golden ribbon here of the signal of a high probability manifold. This is all that the processor is doing. This is our golden path. This is why we need an ADK processor. Create a subspace that is optimized for our operations. Then we have the term flows. The Google definition of a flow in ADK is an ordered list of ADK processes. Simply the pipeline that the data travels through. Guess what? I already showed you this in my last video. This was the gravitational signal coming in from the LIGO detector. Then we had here a constant Q transform. Then we built our time frequency spectrogram. Then we had here the patching and the k-mean quantization. You see an ordered list of ADK processor happening. Great. We understand what is a flow. Our agent math definition. A flow is simply the topology of the probability chain in the probability space where the agent is defined by the new mathematical framework by Google. Great. So, a flow is the code that enforces this particular structure. A flow dictates that before the agent thinks, it must pass through authentication processor, cache processor, memory processor, and so on. So a flow forces the agent to execute the integration path we define in the mathematical optimization. So what it does, it simply prevents the agent from skipping a step or hallucinating based on unverified data. Flow enforces here the magnetic field to have here a compression to the main focus here, the main golden plasma path here forward. This is what a flow is. Then artifacts. Google definition, large data, PDFs or CSV files are stored separate from the chat. The agent only sees a handle, a pointer, not the complete raw data. This makes sense. Our agent math definition in this paper is this is a direct optimization of the cost parameter. So, if you have the objective, hey, maximize here the probability, maximize here the success of my AI system, but not at all costs, we have here a correction term, lambda times the costs. So this is the cost parameter, lambda. So if you paste a 5 gigabyte CSV file into your prompt, you're not going to be happy if you have a 2 million token window because simply lambda will explode. So the agent becomes too expensive to be useful. Now with this pointer, agent only load the artifact, dereferences here the pointer, if it is mathematically necessary for the probability to be a success, therefore a calculated increase in the probability optimization of the mathematical framework. Term 4, narrative casting or multi-agent translation. The Google definition is when agent A hands off to agent B, the system now rewrites the history so agent B understands who said what in the past. So we optimize the complexity of the representation of the communication data for the intelligence level of agent B, so therefore agent B can do the best job of his life. In our agent mathematical definition, this is the optimization for, guess what, the collaboration context, our CL. It can be so easy if you define it in mathematics and then you build your linguistic narrative. Google reality. If an agent A, the supervisor, gives its raw logs to agent B, a scientist, the agent B might get confused because the agent has no idea why the supervisor has to do all this political talk here with the funding agency. A scientist is interested in science, full stop. So therefore, if the agent B, the scientist, gets confused, it lowers here the probability P and therefore the performance of this agent will suffer. Therefore, narrative casting is now the algorithm in the mathematical paper that simply translates the context CL into the optimal format for agent B, maximizing the probability that agent B understands the particular assignment given without any political small talk. My goodness, the world can be such a beautiful and simple place. I have shown you this already in this video just days ago, where I told you, reduce the context for maximum intelligence. Why? And we went here through a complete 40 minutes video. I can't believe it. 40 minutes. Okay, beautiful. But you see, I already explained everything you need to know in this video. So therefore, term 4, narrative casting, check mark. You know it. So what is Google telling us in this new mathematical preprint of today? Don't use raw data. Use ADK processor update function to compile the noise and extract the pure signal of our gravitational wave and update the state as. Second, don't guess the path of our configuration. Do we need 5 agents? Should I connect every agent in a star formation or should I have a logical chain? Use the flows that are defined by Google in the ADK to define here the best probability topology for the job given to the AI. Third, do not ignore the costs, and I like this especially. Use the artifacts in ADK to keep here the lambda parameter low. So this means I define for the complexity of my job, I don't want to spend more than $25 on this particular job. Find the perfect AI configuration with 12 agents, 12 different LLMs from, I don't know, Anthropic, Google, whatever, to do the job. So therefore, here we have it. This is the end of the video. My God, I can't believe it. Yes, we did it. So you will understand here this new documentation, Google for Developers, and all the flow and process and everything if you have read this paper here. Guess what? Google Cloud AI, December 5th, where they tell you here, and they explain to you in detail the mathematical framing for different agent strategies. Those two go together beautifully. I read accidentally this as the first paper, and therefore the second paper was a piece of cake. I hope you do it the same way. I hope you enjoy this. I hope you see which major step forward this means. We don't have to take care about the optimal prompt configuration. We don't have to take care about how we build our multi-agent system. We don't have to define here any tool use. We don't have to build here the communication channels in a star pattern between the agent, supervisor agent, what configuration to choose. According to Google, according to this paper, we have a new mathematical optimization procedure that we just feed this into the machine, and the machine will tell you for a given amount of $20 and the complexity of my job, it will give me the best configuration of machine communication patterns, densities, tool use, whatever. This will not only change the way we code AI, This will change the way we use AI, also for industrial production. This was it for today. I hope you enjoyed it. I hope you had a little bit of fun. There were some new facts and optimization procedures for you. Hey, why not subscribe to the channel? Maybe even become a member. But anyway, I hope to see you in my next video.